Okay, calculus, let's do another one. Sometimes you need to use logic when this test doesn't work. So let's see how that would bear out. Find the relative extreme of the function f of xy equals x squared y squared. Partial derivatives, 2xy squared and 2x squared y. When they're both equal to 0, if two things are equal to 0, they're equal to each other. When is 2xy squared equal to 2x squared y? I can subtract them from each other. Factor out a 2 and an x and a y, and you're left with y minus x. So either x equals 0, y equals 0, or y minus x equals 0, which means y equals x. Now, if y is equal to x, this is 0, or either of those things equals 0. Now, what else do we really know? If y is equal to x, the only way each of these individuals can be 0 is if one of x or y is 0. We know that from here, which means the only thing that ever can work is if x and y are 0, and if we plug it back into the original, z has to be 0. So we've got 0, 0, 0 here. Now again, we need the second partial derivatives to test. Second partial derivative with respect to x is 2y squared. Second partial derivative with respect to y is 2x squared. And the partial derivative with respect to each of these is 4xy. So again, d is the first two multiplied together, so that's 4x squared y squared minus that 4xy quantity squared, which in this case, that's 4x squared y squared minus 16x squared y squared. 4 of something minus 16 of that same thing is negative 12x squared y squared. And we're checking at the point 0, 0. When we plug in 0 here, we get the d equation is equal to 0, this determining equation. What does it say if that's equal to 0 according to our rules? It says this is inconclusive. So how are we supposed to determine if this point is a maximum or minimum? Well, let's consider the function x squared y squared. What do we know about x squared y squared? It's always greater than or equal to 0, right? Because these are both positive. Now, we know that this critical point is at 0, 0, 0. But we know the only things that can happen to our z value are they have to increase. So that means this thing has to be a minimum, just by logic, even without doing the math. We know the point 0, 0, 0 must be a relative minimum. It's actually an absolute minimum. So sometimes you can't use the rules and you have to use your brain to figure it out. And we'll try to avoid some of those if I'm actually testing if you know how to use this. So let's do one more unsavory problem before we do 13.9. Find the absolute extreme of the function f of xy equals sine xy over the closed region bounded by 0 is less than or equal to x, less than or equal to pi, and 0 is less than or equal to y, is less than or equal to 1. So again, partials f of x, it's cosine xy times the derivative of the inside, which will be y. So y cosine xy, partial with respect to y, is x cosine xy. So when is y times the cosine of xy equal to 0? We either need y to be equal to 0, or x times y has got to be pi over 2, 3 pi over 2, but since x is between 0 and pi, and y is between 0 and 1, it's got to be pi over 2. It's the only one in the range. What about x cosine xy? We need x to be 0, or xy to equal pi over 2, because it's still cosine. Okay, so what happens here? how many points of intersection do we have? We've got 0, 0. So since we have both of these equal to pi over 2, we can let x be a free variable. That means y, if we solve for x, has got to be pi divided by 2x, just by dividing the x to the other side, because it'll adjust. I forgot to leave a blank. Oh well. We can have only one of them be 0, so it could be x could be anything as long as y is 0. You would think. Now why is that correct or not? Well, here's the idea. These are boundary points after all, but if y is 0, this thing is 0 automatically. So what does x have to be if y is 0? Well, the cosine is 1, which means the x really needs to be 0 for this to work. So you might think that there's a cross combination there, but there shouldn't be. x0 should not be a combination. So that one's out. You have to check the boundary points as well. Really, all of these are about the boundary points. Don't you always check the boundary points even if it doesn't work, just to make sure it's a relative extrema? So x0, the other boundary point would be x1 blank. Then we would have boundary points otherwise, 0y blank and pi y blank. We'll worry about these boundary points in the end. That would be if we're doing relative extrema, we would have to check those. Since we're only doing absolute extrema, we don't need to check the endpoints. Or, I mean, we do. These would be the relative extrema. We need to check the endpoints since we're doing absolute extrema as well. Okay. So to do this, I need second partial derivatives. fxx is negative y squared sine xy fyy, negative x squared sine xy. The second partial that's mixed is slightly more unfortunate. It's going to require product rule either way, but we'll manage. It can be cosine xy plus xy times negative sine xy, which is negative xy sine xy plus cosine xy. However, arguably, this would be easier to check if we're trying to find what d is, right, at every point. Now, one thing to note, t equals f of xx times f of yy minus f of xy squared. Now, we can even plug in values to check this. So let's check in at 0, 0. What do I know about the point 0, 0 here? At 0, 0, d is going to be 0 times 0. This whole thing becomes 0 plus the cosine of 0, which is 0 plus 1, which is 1. 0 plus 1 is 1, which means 0 minus 1 is negative 1. So d is negative, x is 0, 0. We don't know if it's positive or negative. So that makes it somewhat inconclusive. We'll continue this in the next video.